our session, let me introduce Dr. Debdeep Sarkar to all of you. Dr. Debdeep Sarkar has done his PhD and MTech in electrical engineering with specialization in RF and microwave from IIT Kanpur in the year 2018. He has done his PhD, and in the year 2013 he has done his MTech. He has also worked as visiting researcher and postdoctoral fellow in the Department of Electrical and Communication Engineering, Computer Engineering, Royal Military College, Canada. And he has also served as assistant professor in the Department of Electrical Engineering, IIT Ropar, from March to July 2020. And currently he is working as assistant professor in the Department of Electrical and Communication Engineering, Indian Institute of Science, Bangalore. And his current research areas include MIMO antennas, radar systems, space-time varying metasurfaces, antennas in the near field and energy analysis, ultra-wideband and multiband systems, correlation analysis and channel modeling, computational electromagnetics, FDDT. So also I want to add that he, at a very young age, he has achieved so many things. He is just a role model for all of us. He is very young, but in the field of research and in the field of antennas, he has achieved a lot. I must say that after attending his session, you will be inspired very much by him today. So please listen to him and please take inspiration from him. Please take something from today's session. So over to you, sir. I welcome you, sir.
Yeah, well, thanks very much, Dr. Priyanka, for the kind introduction. I mean, you for the nice words of encouragement. So yeah, I mean, let me share my screen and then I'll like start.
Yeah. Yes,
so, yeah. Okay. Yeah, just let me know if you are like there is any issue. You can see my screen, right?
Yeah, I can see.
Yeah. Okay. It's good. So, and my voice is also audible properly, right?
Yeah,
there is no issue.
Okay,
okay. Thanks very much, Dr. Priyanka, for inviting me here in this FDP. I saw from the brochure that it is really well organized, and I could see many stalwarts participating and also contributing to this FDP as speakers. So I could not attend the inaugural ceremony, but yeah, so today is I actually chose this date after discussing with Dr. Priyanka, because Sunday, but anyway, Sunday morning might not be the best time to discuss too many things about electromagnetics and antennas and stuff like that, but I'll try to not bore you, and I try to give as much information as I can, and maybe like after this talk, you can be motivated to one of the different areas or many areas that I will be sharing today. So initially, I thought that I would keep the topic as, MIMO radars only, but later on when I saw the complete scope of the FDP, then I thought it is better to make it more general. And I also added, some of the work that I did on MIMO antennas, some like research during my PhD and postdoc. So that part I added. So feel free to, if any point at any point during this talk, I'll especially request to Dr. Priyanka that if I am not audible or any problem is there, just feel free to, I'll keep an eye on the cell, and you can just drop me a message in WhatsApp and stuff like that, because sometimes, I'm giving this talk from my apartment, so sometimes there is a problem in the Wi-Fi and stuff like that. So just a heads up on that. So anyway, let me come to the point. So the title of my talk today is MIMO antennas and radars and an electromagnetic perspective. So that I'll try to present. So before going into the main agenda of the talk, I'll share a couple of things. First of all, I'll discuss a little bit about my lab at IISc, which I call it the Laboratory for Innovation and Development in Antennas, Radars, and Electromagnetics. So I call it IDARE. And we aim to, as you can see, we aim to resolve problems on antennas, radars, and general electromagnetics, which could be classical. And of course, nowadays we are looking into quantum electromagnetics and the concepts like quantum radars and all. So which are relevant for the next generation information and communication technology healthcare, security and defense, and energy sector. And we carry out research in component level, in algorithm level, as well as system level. So it's not like single faceted. There are different sides to our overall research vision. So details on that, you can visit my web page. I have mentioned in the bottom, you can see. You can visit there and you can see and like maybe give some feedback through me through social media and stuff like that. Anyway, so I'd like to acknowledge the Infosys Foundation Bengaluru for conferring me this Young Investigator grant. We are carrying out some specific research based on that. And we are also having ongoing collaborations with several institutes in India. One of first and foremost is currently IIST Trivandrum with Dr. Chinmay Shah and many associated people over there, and AD, and Aeronautical Society of India, NRSC Hyderabad, SAC Ahmedabad, and also IIT Indore, and many other institutes. We are currently, extending our collaborative hand to them, and we are currently working on a number of joint projects. And some of the international collaborators are, of course, RMC Canada with Professor Yahya Antar and some of other colleagues belonging to Queen's University Canada, and more to come. So this is the broad research vision that we are having at IDEAR. And now I will just, before coming to the technical part, I will just talk a little bit about the IEEE Antennas and Propagation Society. And because I am currently a part of one of this IEEE AP Society Young Professionals Committee. So as you can see, AP Society is having consistent healthy growth in the past several years, and it's 13th out of the 39 IEEE societies in size. It has close to 10K members, and you can see that the student membership is growing, how many chapters are there, and we are expecting more growth. And we are belonging to the region 10. So that is also a huge contributing factor. You can see from the data that how many members are there from region 10 itself. And you know that there is several volunteer opportunities. We are an international society, and we are looking forward to increase the diversity of our members and volunteers, because the society, like all other IEEE societies, AP Society is also run by volunteers. So we need a wide range of activities, starting from the administrative committee, leadership, journal, symposia. You can see the list over here. So we are in lookout always, we need your active participation and representation, including the young professionals and women engineers and industry engineers from all sides. We need the volunteer association. And this is the committee that is headed by Dr. CJ Reddy, Vice President in Altair Electromagnetics USA, is the chair. And there are, you can see that among the members, there is representation from different parts of the world, and also the diversity aspect is also taken care of. I think you already heard from Nasser yesterday. So there are, you can see that we have Asimina, we have Constantina, antenna engineers, and also we have Kamar and Nelson and Professor Andrealu. So it is a diverse group currently, and maybe it will also expand and get changed in future also. So this is some of the things that some of the initiatives that are taken by the YP committee. There is a YP column in the Antenna Propagation Society magazine, APS magazine. In June 2021, there was one article written by myself, and which is Antenna Learning and Research for Students and Young Professionals in the Post-COVID-19 Era. So maybe you can have a look on that. And just in this month's issue, August 2021, there is an article by Nasser on Dare Mighty Things and Fly on Mars. And you can see that there are some articles that are in the pipeline. So, and like before I go into the technical part, there is one more information for all the antenna engineers out in the audience, that we have started this APS Young Professional Ambassadors Program. So you can visit the website that I have, presented here. Like this website you should visit, and there is the details. The subcommittee chair is Dr. Kamar Abbasi from University of Glasgow, UK. So the framework has been formulated, and the deadline for nominations is this. And like you can see the more information about the ambassador program. And I would like to invite you all who think that you have the requisite, the background and the things that are required, you should definitely apply by the deadline. So it is a way to reach out to more and more antenna propagation society young professionals who are scattered all around the globe. So this is one information that I wanted to share with all the participants and aspiring antenna engineers. Now, after all this introductory part, I will come to the main technical side of my today's presentation. So first of all, this is the general structure that I have kept, starting from antennas in wireless communication, and how actually the antenna engineers or the antenna research has helped from during this evolution from the 1G to 5G and beyond. So what is the role of the antenna engineers in this journey? Secondly, I will come to the antenna aspects in the MIMO systems, like the handsets and base stations and the access points, and discuss about some of the research that we have done, both in the design of the different antennas required for the MIMO systems, as well as the correlation coefficient, and little bit more on the analytical side, like evaluation of the correlation coefficients from antenna currents and some of the functions that we try to introduce, like cross correlation Green's function. So why that is needed. And then I will talk about another aspect, like while MIMO antennas, this is mostly for the wireless communication point of view. So there is another concept of MIMO radars, which is very much relevant in the present day, especially in the context of the automotive industry. So the concept of MIMO radars and some of the research that we are doing here at IISc, that I will be discussing. And then a little bit before conclusion, I'll try to give little bit insights towards some of the fundamental research that is relevant to all multiple antenna system. Okay. And the near field energy distribution around this system. So these are like the kind of the different aspects of the research where I am part of. So to start with, I'll discuss about the role of antennas in wireless communication systems. And communication is the process by which information is exchanged between the individuals and computer systems through a common system of symbols, sign, and behavior. And we generally try to classify the communication systems into like wired and wireless. So wired communication, you can think about the telephone connections, earlier days, wired cable based connections. And also it's not necessarily electrical wires. It can be any guided medium. Like it can be, we can classify the guided medium communication as one of them. And of course, the optical fiber technology is a prime example of the power of the guided medium, which is actually the backbone for many like networks that we are currently experiencing these days. Now, wireless communication is when the electromagnetic transfer between transfer of information between one or two points that is not using any guided medium. It is happening, it can happen in free space, that is in complete vacuum, without the presence of any medium, it can happen. And also, of course, in the presence of medium also, there will be certain change in the property of the electromagnetic waves, maybe that is propagating through the medium, but that can occur. That is, there is no specific guiding link between the transmitter and the receiver. Then we can say that it is a kind of wireless communication. Now, early days of wireless communication, it like theoretical framework was there, but experimentally, it started with the Henry Hertz's classical experiments, which were conducted in his laboratory using a small, the end-loaded dipole that is driven by an induction coil and a spark gap. You can see from the figure that we have this induction coil, and that is actually giving a spark at this end-loaded dipole. So when you are having this spark, it is actually creating some electromagnetic waves, and that wave is inducing another small spark in this receiver coil. So receiver was a small loop, and the detection was by induced sparking. So this, you can say that this is one of the early examples of the wireless kind of exchange. Like there is a spark that is induced at the transmitter side through this induction coil, and that is detected at a distance. So the frequency generated by the spark transmitter is determined by the resonant mean frequency of the antenna system. So basically, this, you can say, paved the way for the communication links that we are having these days. And details from this figure you can find from this particular link, and many more information about this experiment, the frequency range and the corresponding wavelengths and other details you can see from the link that I'm having below. From Indian point of view, we should not forget the contribution of Acharya J.C. Bose on the early electromagnetic wireless communication. So he gave the first public demonstration of EM waves using them to ring a bell remotely and explode some gunpowder. So you can see the sentence that was, or the phrase, the sentence that was mentioned in Daily Chronicle of England in 1896, that the inventor J.C. Bose has transmitted signals to a distance of nearly a mile. And herein lies the first and obvious and exceedingly valuable application of this new theoretical marvel. And Bose described to the Royal Institution in London his research carried out in Calcutta at millimeter wavelengths. And from this particular MTT paper, you can find out the details like his role and in the 100 years of millimeter wave research. So interestingly, he used waveguides and horn antennas, dielectric lenses, various polarizers, and even semiconductors at frequencies as high as 60 gigahertz. And we are now, like in many of the 5G things, we are looking for at these frequency ranges. So interestingly, some devices and some of the early research was carried out in this particular frequency ranges, 60 gigahertz, and the high frequency regime as early as this 1895 or 96. So you can imagine his genius at that point. And also we should remember the contributions by Marconi, who achieved a transmission distance of 2.5 kilometers by using earth and an elevated aerial at both the transmitter and the receiver. And the Marconi antenna, you can see, typically the Marconi antenna is nothing but, in present terminology, we can call it a typical quarter wavelength ground plane antenna. So this is the picture. You can see that this is the quarter wavelength vertical radiator, and this is the coaxial transmission line that is actually exciting it, and these are the ground plane type of rods. So instead, it is not a constant like a continuous kind of ground plane. There are these 4 rods that are sitting over here. So anyway, details about the antenna that Marconi used and his experiment, all those things you can find out from this website, and there are many other resources also available. So this is the kind of background I was trying to give for the wireless communication systems we are having. But now we talk in the terms of 1G, 2G, 3G, and 5G, and now people are talking about 6G and stuff like that. So if you think about how all these things evolved, so we can go back to the portable AM/FM radios, which were actually military grade, and that was in the time of the Second World War. But that is not in the civilian domain. So we generally do not, talk about it in terms of all these generations and stuff like that. So typically the 0th generation or 0G, that is generally referred to the commercial mobile telephone service introduced by Bell system. But that mobile telephone service is not exactly the mobile that we hold in our hands nowadays. It meant that communication between vehicles, like intra-vehicular communication type of things. Like, I mean, it could be some cargo carrying, or maybe some ambulance contacting wirelessly to a nearby hospital or something like that. So it is a like mobile means it is on some vehicle. So that we generally talked about is as the zeroth generation. When we think about the first generation, that we go back to the 1980s, where you can see the portable cellular phone or a handset that is actually present with some businessman who is talking at the airport, Chicago airport. So this is the journey. I mean, starting from the military grade thing, we are now having a smartphone, like maybe looking like this, which we have with us. So, and which has different features. By different features, because nowadays we think of it, the smartphone, not only as the voice telephony kind of system. We have the texting capabilities, we have the capability of taking pictures, high definition pictures and videos, and sending them to our friends. And also it can do a lot of like other processing, which requires like a lot of data handling through different applications or apps that we are having with us. So you can see the evolution from this 1G to 5G. Of course, in all this technology, there is a phase for the research and standardization, as I mean, pictorially, I'm trying to represent through this. And there is a phase for the commercialization of the technology that is there. But the journey, if you see, starting from 1980s to present generation, when we are looking into, we are evolving in terms of the data handling capability a lot more. We are the smartphones can handle a lot of data exchange in it. So essentially, the data rate, we can simplify it. So how that is made possible? What are the technologies that are behind it? And not only data rate, there is also an issue of the error-free transmission. I mean, error-free transmission, and we should also look into the reduction of inter-user interference and stuff like that. I mean, data rate is just one aspect. So all these things, our technology is evolving. And when we are talking about fifth generation systems, what are the major objectives when we think about the 5G? So 5G new radio, I have taken it from some internet source, that it is not only like, there is one aspect you can see, which is called as the enhanced mobile broadband. So this aspect of 5G is relevant to extreme capacity and extremely high data rates and stuff like that. I mean, you can see the multi-Gbps peak rates and 100+ Mbps user rates. And capacity, we mean how many like per kilometer square, what is the total, like 10 Tbps per kilometer square. This is the type of capacity people are envisioning for 5G. But is this data rate the only thing? It's not. I mean, there are several other aspects also, which may or may not be like exactly overlapping with the data rate part. So for some cases, we are like, there is two more things. One is the mission critical control, or ultra reliable low latency communication systems, where we actually look into a reliability like this, probability of error less than 10 to the power -5 per 1 millisecond. And we have the ultra low latency as low as 1 millisecond. And strong like security, the secure part of it is very important. So that those things are needed for the mission critical control. And there also we need the user mobility. We have to support very high. I mean, the people are looking into up to 500 km/h, people are saying. And not only that, this is the URLLC part, this is the EMBB part, and we are also having the massive Internet of Things, where we are looking into the deep coverage, where we can reach challenging locations, and we can have the ultra low energy, that is the battery life. We need to ensure that it is very high. And at the same time, we also want to make these systems, that the Internet of Things, that are like huge connected array of different objects, you can say, like connected to the Internet of Things. So the density of the nodes can also be very high. So these are the things you see that sometimes why I wanted to make this like difference or contrast time and again, that sometimes we may need very high data rate, but maybe for the Internet of Things, we need high connectivity, may not be very high data rate requirement, may not be there. So the antennas, the backend algorithms that will be needed, those things are very much different when we look into something like developing a high data rate access point or mobile communication link, and when we are looking into developing the antenna or sensor systems for the Internet of Things. So depending on the application, the requirement of the antennas, the specs will actually change. So that is one important issue I wanted to highlight. And this is another way of looking into this 5G hyper service. So it is an axis type of representation. Like you can see that on one axis, we are having the number of links per kilometer square, another axis, the throughput in kbps per kilometer square, and in another axis, it is the delay in millisecond. So you can, very grossly, you can map from this to this, like this links per kilometer square is maybe you can map with the Internet of Things part. The throughput you can map with the EMBB part, and the delay you can map with the mission critical controller URLLC part. And one more thing that should be added, there should be the backend compatibility. That is, you can see that where the 2G, 3G, 4G are also lying within this 5G hyper service queue. And there are several functionalities like this multi-user UHD telepresence and augmented reality and smart city, smart sensor, many healthcare. Healthcare, of course, is one of the very important area. So in this context, when we are talking about 5G, in Indian context, there is this 5G testbed project running, and I think it's coming to an end probably this year. And we have like different partner institutions in this 5G testbed project by Department of Telecommunication, Government of India, that IIT Madras and IISc and CWIT, IIT Delhi, IIT Kanpur, IIT Hyderabad, and Summit Chennai. They are all taking part and focusing on different areas of this 5G testbed project. So you can see that some of the focus areas, so this has been taken from the IISc web page, that there are different areas that IISc has looked into, that sub-6 gigahertz baseband algorithm development and millimeter wave beamforming and V2X communication, that is from vehicle to anything, and then visible light communication. So there are different aspects of this 5G technology. I cannot, like, there is not a single description is not there to define what is 5G. Like different things come into the picture when we talk about 5G. So far we have talked about the 5G. Now the question is, why MIMO in the context of this enabling technology or for 5G? So as I was mentioning, that data rate aspect, you can see that when for the third generation of the systems, we were actually having a data rate somewhat of this order, 384 kbps. And then slowly people started moving into the MIMO systems. And there was the single user MIMO, multiple user MIMO, and also the massive MIMO that is coming into these things. So why this multiple input, multiple output technology, why it is this much important? This is important because in any communication link development, we have certain resources, right? We are having the spectrum requirements, that is, we cannot judge that, being designers, we have to conform to whatever is the approved spectrum for a certain device. And there are sub-6 gigahertz bands and millimeter wave frequency ranges, which are currently specified for the 5G. Now, when the total band is allocated, it is not that we can use the entire band for our device, because the available bandwidth is again limited by the different components in the transmit and especially in the receive chain. So the overall bandwidth might not be as wide as we may think from the overall spectrum approved for our operation. So in short notice, that in a short nutshell, we can say that we cannot go beyond a certain bandwidth to operate. And we know from your like undergrad level Shannon channel capacity theorem that if you increase the bandwidth, you may be increasing the capacity. So very simply speaking. And then another aspect is, can we make the signal to noise ratio even more higher? But we cannot transmit also beyond a certain power because of the safety requirements. There is a specific guidelines, and eventually our objective is to tone down the used power and go towards the greener and safer communication system. So essentially, we have to operate within very stringent limits of the bandwidth and also the power level. And at the same time, there are ways to operate in these regimes and to use the higher order modulation schemes, but that also might not be feasible for many cases. So if we try to operate within a smaller complexity of the signal processing algorithms and also work in the constraints of the power and the bandwidth, engineers actually developed this technology for using multiple transmitters and multiple receivers. So the complete chain looked something like this, where you have the transmit data and we have the encoder and interleaver and serial to parallel converter. And from here, you can see that it is basically representing 16 transmitter antennas and we are having 4 receiver antennas. So there should be some feedback, that is the channel state information from the receive antenna we must have here, and that will decide what type of transmit weights we are going to use, and we are going to pre-code our data or maybe do the respective beamforming. I'm trying to talk in a very simple way. So using multiple antennas at the transmitter end and multiple antennas at the receiver end enables us to use some additional signal processing algorithm, which in turn helps us to work or alleviate these limitations that we are currently having in terms of the bandwidth and the power requirement. That is, for the same available bandwidth and the amount of power, we can actually enhance the overall available channel capacity. And that will, there are many aspects to it. There is the concept of array gain and diversity gain and multiplexing gain. So all these things have to be evaluated and optimized in a proper way so that we can get a very good performance out of your MIMO system. So I'll just go briefly through it, why we wanted these multiple antennas, because mobile and wireless terminals, are subject to strong fading due to the multipath propagation, and especially when you are using in urban and indoor environments. So when you have the multipath propagation, the performance of the terminals in such environments can be significantly improved by making use of spatial polarization and pattern diversity. This means that the signals on, let's say, the 2 antennas with different position, polarization, and radiation pattern are combined in such a way that there are shallower fading minima. So that actually enables us, if you are having, let's say, your receive terminal, it's having more than one antennas, then you can actually realize a shallower fading minima by means of the different position, polarization, and radiation pattern. So when the 2 antennas have different polarization, we call it a polarization diversity. When their beams are pointing towards different directions, we are calling them a pattern diversity. So these are, very simplistic description. So effectively, this corresponds to when we are having a shallower fading minima, this is effectively corresponding to an increase in the signal to noise ratio in the fading dips. So the fading margins in the system link budget can be reduced. And this increased SNR can alternately be used to increase the capacity of the communication channel if the system allows this. So, I'm trying to approach to the, or converge to the same point from different directions, that ultimately this is a system level. When we are calling it a MIMO, it is actually a system. Multiple input means multiple transmit antennas, and multiple output is the multiple receive antennas. And overall, we are having a MIMO system. So the channel capacity part, I have tried to explain in a very simplistic manner. So this is only this particular picture is valid mainly for the point-to-point MIMO systems. So in point-to-point MIMO systems, we are not looking into the beamforming aspect in the transmit part. That I can say, in a simplified way. So you can see how it is being changed. So let us say we are considering a communication link that is having one transmit antenna and one receive antenna. So in that case, the channel response, we can define it as a scalar quantity and scalar h that I have written over here, and the capacity per bandwidth. So it is actually, the unit is bits per second per hertz in this case. So bandwidth aspect is actually divided by. So it is log to 1 plus pt upon sigma n square. So this is actually the, whatever transmit power is available divided by the noise level. So it you can say that it is the SNR part. So, and it is product by this mod of h square, where h is your scalar channel response. Now, when you have multiple transmitters and when you have the multiple receive antennas, then essentially the channel is no longer a scalar quantity. It becomes a matrix, and we represent it by this bold capital H. And in that case, you can, after many calculations, I have skipped all those parts, just the final thing, you can actually represent the overall capacity, something like this. So log 2 is there, and now you calculate the determinant of this complete matrix. What is this complete matrix? On one side, you have an identity matrix of dimension MR. MR means that MR into MR, MR number of receive antennas you are having. So this is the identity matrix, and another matrix is actually getting by the H multiplied by H Hermitian. H is your channel matrix, and the superscript H is actually representing the Hermitian operation. Hermitian means you take the transpose and you take the complex conjugate of all the elements. So essentially it's a complex channel because we are representing the amplitude as well as the phase. It is in the phasor form that we are delving in. So when you have expression like this, it is not always you can ensure that it will give you a capacity enhancement, but in certain condition that when this channel matrix actually is a full rank one, then you can say that, okay, we are going to have enhancement in the overall capacity multiplied by, from the SISO link to the MIMO link, it is multiplied by the rank of the channel matrix. And rank means if you consider the minimum of the number of transmit and the number of receive antennas. So let us say, just for numerical example thing, that you have 10 transmit antennas and 4 receive antennas, then your channel matrix, you can say that, okay, it is 10 cross 4 or something like that. And from the 10 cross 4, you can actually find out the rank. So it will be like, if it is a full thing, that is, there is no rank deficiency in the system, then it will be 4 times. So you can get a 4 times enhancement. If it is a 10 cross 10, then you can get 10 times. It is not that it is, if it is 10 cross 10, you will get 100 times. It does not work like that. So essentially the channel, to make it full rank, you can see that there are situations when you have to go, like, it actually gives the best performance in terms of the non-line of sight things. That is when you have non-line of sight and there are several fading paths and stuff like that, then you can get a full capacity enhancement. But in line of sight case, it might not be, giving you the full rank. There could be one dominance, like it becomes more and more close to the Rayleigh channel rather than the Rayleigh fading scenario. So, well, I will not go into all the details about the communication aspect in this particular talk because we have limited time. So, but I just wanted to give you an idea like how the capacity enhancement works. It is, sometimes you may be tempted to think that if we have, let's say, empty number of transmitters and MR number of receivers, then empty into MR times capacity is getting increased. We may be tempted to think, but that is not the case. It depends on the channel matrix and its rank and stuff like that. And this is also, this particular figure is also a simplified case where we are considering a point-to-point MIMO link, and the channel, again, we are referring it to as a Kronecker channel model. So why this Kronecker model is important? Because it helps us to understand the effect of the antennas on this complete channel matrix. So we are so far discussing that, okay, we have come to the, let's say we agree on the fact that we need a complex channel matrix and we need to tailor the channel matrix in a proper way to get the best performance out of the system. But what is the effect of the antennas on the channel metrics? How they matter? Because you may normally, if we think from the communication point of view, you can think that okay, it is the IID relay channel, and the thing that I mentioned over here, that independent identically distributed elements with Gaussian distribution, let's say, as the elements of the channel matrix. But now, if we let's say think about the effect of the antennas on the system, that actually comes from the correlation and the mutual coupling between these different antenna elements, like how these antennas themselves are talking to each other. We can ignore the effect of antennas only if the antennas have very negligible coupling and negligible mutual interaction, you can say. Only then we can fully exploit the properties. If the antennas are themselves coupled or their patterns are correlated, okay, in that case we will not be able to, even if we are using multiple antennas, we will not be able to get the best performance out of the system. So that is why characterizing the correlation, and maybe if the correlation and coupling between these multiple antennas, both in the transmitter side and the receiver side, are important. And how, what is the parameter that actually controls this? One quick thing is, if you place the antennas closer, definitely there is going to be some mutual coupling. So how to, people have done research on how to reduce the mutual coupling between two closely spaced antennas. And that is a very, important area or important research direction, where we use different technologies like the neutralization lines, or maybe sometimes a defected ground type of structures, so that we can reduce the space between the antennas, and that actually helps us to reduce the form factor of the overall system. So these are interrelated aspects. So the impact of antennas I was just trying to highlight, and not always we can place the antennas far apart. And even if we are placing the antennas close together, well, it can happen that we might be able to change the polarization of the nearby element in a way that it gives you the polarization diversity. So these things I'll be touching upon. So some of the things that, let's say, from one example, instead of saying in language, if you see the example that how the cell phone handsets have evolved and accommodated these multiple antenna systems, which lead to the diversity. So this can be, you can say that this is the cell phone picture, or the picture that I showed you from the 1980s, the Motorola handset. So there, essentially, this is not the exact figure of the antenna that is represented here, but just the concept of sleeve dipole I wanted to highlight. So sleeve dipoles were used, and there was a single antenna. But now we are having these inverted F antennas, which are based on the printed circuit boards, and which are actually, you can see that in the GSM frequency range, in the lower band and the higher band, it is there. But additionally, we have another diversity antenna. So this is taken from the antennatheory.com. And so you can see that this is the main antenna, main transmit receive dual band inverted F antenna. And additionally, we have a diversity antenna. So that will, if by in conjunction with the proper combining techniques and the proper algorithms, it can enable you to reach almost twice the capacity that was there for a single antenna system. So this is generally called, because the two antennas, they are separated by space, but the pattern and the polarization of the two antennas might not be very different. So, but since they are spatially separated, this is known as generally the spatial diversity. Because of the spatial difference, it will create some phase change in the phase, and that will change in the correlation between the two antennas, and that gives us the spatial diversity performance. So you can see that they are certainly main antenna and this one, they are far apart. But this is another handset where you are having two inverted F antennas with different polarization. We can call that if I'm holding the cell phone like this. So this element may be called as the vertically polarized element, and this one as the horizontally polarized element. So, but in this case, these two antennas are placed very close together, one edge of the thing. So these are some of the examples where you can see that this is the polarization diversity. that is there in the smartphone handset. And right now people are also looking to, as I said, it depends on the number of receive antennas, like the data rate and all the channel capacity. The rank of the channel matrix is dependent on the number of antennas in transmitter and the receiver. So the idea is that if we are somehow able to increase the number of receive antennas, because a number of transmit antenna, if it is in the base station side, we can maybe able to increase it through the massive MIMO and other techniques, which I'll say in a moment. But the receive antenna, the number of receive antenna, well, the handset size is limited and very little amount of space is often available. So there is a significant research that is going on nowadays, and many of my colleagues in different institutes and also who are doing PhD, they are working on developing such compact. So this is just one of the example that I have given over here from one particular paper. But there are many such papers now, and like open literature as well as patents and all that are filed on this particular topic, that how to accommodate this number of antennas so that they are having very less mutual coupling, and at the same time they can give you some diversity in terms of, let's say, polarization or pattern. If that keeps, then we can actually help to increase the overall data rate and the performance of the complete MIMO system. Now from the handset side, if we slightly change our viewpoint to the base station side. So one thing I should say here, I was referring to base stations as the transmitter and handsets as the receiver, but that is not the case. I mean, that might not be always the case, because the handsets will also communicate to the base station. So in that case, they will act as the transmitter. So it is overall, you can say that the transceiver system. Anyway, so base station antennas typically, if you look like this particular paper I have referred, you can see that they're typically 1 to 2 meter with gains of 15 to 20 dBi and placed in towers between 25 to 75 meter above the ground. And one of the important properties that they have to be high aperture efficiency and power handling capacity has to be more. And the idea is that we need to have because the sector based communication system, so sectorial coverage should be there, and the dual band and the multi-band properties, they should be there, and diversity. So this is why I mentioned that part, that the concept of diversity that I showed in the handset, which may be coming a little bit later, but that was already there for base stations to combat the multipath fading. So the concept of diversity in smartphones may be introduced more recently, but in the base stations it was introduced earlier. So you can see that how they evolution of the base station antennas. Initially, we looked into designing this omnidirectional type antennas in 80s, and then in 89, we are looking into this sectorial coverage where we have an array of these dipoles. So next, when we make it cross dipole, then it is actually dual polarized element, and we can use a duplexing filter here, so that we are now having receive main path and as well as a diversity path is enabled. So we can actually combine, we can actually combat the fading, because base station is located at a fixed place, let's say, and it is also not moving, let us say. But the user may be moving around, and the signals from the user may be bouncing off the different paths and creating the multipath. So again, to combat that multipath effect, we need to have this diversity concept in the base stations as well. So this was there. And now this is, I was talking about the uplink part, that is the user is trying to communicate with the base station. But when the base station is trying to communicate with the user, it has to steer the beam. And this is the vision, when we are moving from the fixed beam to the full dimensional beamforming, that is azimuth and elevation. So elevation beamforming might be there, but additional azimuth beamforming and things like that, we have to be enabling. I will show you in the figure, and how it is different from the context of 4G and 5G. So what people are trying to envision is, if we are having a control over the entire amplitude and phase distribution on the aperture, let us say the complete aperture is complete aperture of the array is made by these small antenna elements. So each of these elements, so I can excite with a particular amplitude and phase, and if I have a control over all of them, then I will be probably be able to get the beam in different direction. Like this, so essentially, it is the concept of the active phased arrays only, and extended to a massive scale. Like from antenna engineering point of view, it is like that. But how to again operate over use the scheduling algorithms and the networking algorithms, and also the pre-coding, and like how we apply the complex weights to your signals. All these things, all the research that is mainly in the purview of the communication system design. So I will refer like one of the very fundamental books on these large MIMO systems, which is now called the massive MIMO. So this technology was actually, you can say that the inception of it was here in India and in ISC. Like they were one of the leading groups among the different parts of the world as well. But they actually led this particular area of research. And this book, you can, I think, mostly from Indian point of view, you can say that you should follow or try to see this book, and to get a complete idea about that. It's not an antenna book, but it is more on the how to realize the complete communication system using such a large base station array configuration. But from the antenna point of view, this technology of designing large arrays is there, and it is might be being used in different aspects of the other communication system, let's say the space or the, but in the cellular communication system, these large or massive MIMO antennas, they have like brought in one of the very interesting dimensions, that is this full dimensional beamforming. So which I would be like I try to represent over here. So this is typically the beamforming that was there in the 4G sectoral antennas, where we only are having the azimuth or the horizontal beamforming. So in the elevation plane, you can see that it is a wide beam kind of thing. But when you are using these large arrays, so you can actually enable a full dimension, that is the elevation as well as the azimuth scanning capability can be there, and you can actually pinpoint or local do that kind of localization and tracking kind of thing, and pinpoint the user and communicate with them. So that helps in a way, because there is not much spillover, and we can actually work around the user interference, and we can communicate in a more precise way. So these are the advantages that people say in terms of the massive MIMO. But at the same time, there is a worry that if I am going to use such high gain antennas, so what is the radiation hazard and all those things? So that is there. But the point is, the idea what comes behind this technology is, if you are using the number of antennas, let's say, then you will be increasing the gain, and then you might not need to transmit more power. You can actually bring down the power level. So if, of course, you are keeping the power fixed and you are using the high gain antenna, of course, there will be increasing the power. But at the same time, if you are smart enough and you are actually lowering down the power, that will help you to go beyond the, this move towards the greener technology and consume less power, make the systems more resilient, and at the same time you can achieve the focusing and all those things. So the technology is there. How people are going to use it, that is entirely a different issue. So I will keep it there, and these are some of the architectures that are actually used for the massive MIMO, like all the functionalities that I described. I mean, there are many papers, but this is one paper which seems easier to me to maybe explain. So you can see that this is called a turning torso architecture, and it actually accommodates 144 ports. And the details of this you can maybe find out from this paper. I will not go too much, but the idea is that people are using high gain patch-based, microstrip patch-based sub-arrays. This is for the sub-6 GHz frequency range, 3.5 GHz. So microstrip patch-based sub-arrays, and all the sub-arrays are look like positioned and then stacked in a way that it gives you the full azimuth and elevation coverage. So let me just little bit briefly discuss about some research that I did on the access point type of MIMO antenna. So I described about the handset and the base station. So those things, those research I'm currently focusing. Maybe there are 1 or 2 slides on that also. But initially, when I started my PhD with Professor Kumar Vaibhav Srivastava from IIT Kanpur, one of the problems that was there in my PhD thesis was development of these 4-element MIMO antenna configurations. I'm sure many of you who have worked on the MIMO antennas, you have encountered this type of structures for the access point application. So the idea was we need to design this 4-port system which have the pattern diversity and the sectorial beams, as I have illustrated over here, and gain around 4 to 5 dBi and some high isolation and low envelope correlation coefficient. As I said, that the correlation coefficient between the antennas has to be minimized. So low envelope correlation coefficient and compact footprint at the same time. Frequency bands, which were our target, was this 4G LTE and the sub 6 gigahertz bands. So we tried to make the antenna design in such a way that it operates in these frequency ranges. So first we started by designing some of the miniaturized multiband elements. So we were working on some techniques to use the resonator loading on different printed antennas and get multiband performance out of that. Then we tried to bring in those antennas close together and see that how it is operating. But then we found that that approach is actually not giving us the best solution, like because this multiband performance that we got from a single antenna system, a single antenna, when I am trying to bring in more such multiple antennas, multiband antennas close together, the entire property of the system is, going haywire, and sometimes like we have to again change from the. So the idea, what I found later on, that design in situ, that is take the complete form factor and optimize the individual antenna elements on the complete system on the 4-element configuration. Then we might be able to use some of these induced modes in the complete connected ground plane type of system. So one of the things I just try to take you through the design idea, which I explored later on and tried to simplify it in some way, that if we think about designing this 4-port configuration from, let's say, only the dipole, because dipoles we study in our textbook, and we can start from a 4-printed dipole-based system that these are fed at this center-fed half wavelength type of dipoles, and we fix these sides, that is the substrate dimensions. So then I choose the lens in such a way that we have an operating frequency around 4.7 gigahertz, and this is how the radiation pattern from the 4 ports at this 4.7 gigahertz look like. Then I try to modify the shape of the dipoles. You can see the change. That one thing is I try to make one of the arms fatter, and this another arm I try to make it L shape. And in the process, I try to connect also the ground planes, because there is a statement in many papers that are there, because to have the proper DC referencing, you need to have operate all these dipoles or all these antennas, whatever antennas you are using, in a common ground plane. So it is better to do like that. It may be working also without that, but it is better to go for the common ground plane. So once we do that, you can see the drastic change in the scattering parameters of the system just by changing the ground planes, making them more fatter and changing the shape of these elements and connecting them. Previously, these 1 and 2, that is the side-by-side elements, they were having less coupling, and 1 and 3, the diagonal elements, they were having slightly more coupling because of the spatial diversity. But when we are connecting the ground planes like this, the current flow and all those things are getting changed. So effectively, we are actually now having a very more, like the coupling between 1 and 2 is more, and 1 and 3 is actually less. So the patterns are somewhat looking like this. So there is less amount of back radiation, as you can see. And then the same concept we tried to, like, this was just a conceptual thing that I was trying to present. So you can actually use the microstrip fed inverted L monopoles, and you can get them connected. So you can notice, like, from here to here, the frequency of operation has changed. Although this LS, this dimension is same, it has changed, and we can observe that there is a combination, like there is a wideband kind of operation. So this is actually reflected from this microstrip based monopole antenna technology. and we developed it. So we designed it, also fabricated, and got the measurement, and the result you can find out from our, almost 4 years back, this was published in AWPL, and we got like a significant size reduction, and simultaneously the impedance bandwidth was enhanced to a certain value, which was better than other state-of-the-art papers at that time. So then we also extended that work by using our resonator loading kind of idea, and we tried to get coverage of some additional bands which were not covered in the earlier design, and just tune the design in a different way. So this work was also reported back then. Now, while doing all those designs, one of the important steps that we had to do, like, and everyone has to go through, is after measuring the scattering parameters, after going through the radiation pattern measurements, all those things, we also need to see that how the correlation coefficient is actually varying with frequency, and if, let's say, we are for a single frequency also, how to evaluate the correlation coefficient. So there are different ways, as I was briefly mentioning previously, that how to characterize this signal correlation and how that actually maps into the antenna correlation. So when we talk about signal correlation, it is actually the correlation between the received signal vectors. And then when we talk about the channel correlation, it is the instantaneous correlation of the channel between the two fixed locations. But when we are looking into the pattern-based correlation, then we are formulating it with respect to complex pattern functions. So it is not that these things are completely unrelated, the way I was saying. If you start from by evaluating the channel correlation, then starting from the signal correlation, you can actually find out how that is related to the channel properties itself. And when we call it the channel reciprocity. So these are some of the things that you have to, if you go through any communication standard MIMO communication textbook, you will be able to find out. And from the channel correlation part, we then define the fading correlation by actually doing the averaging. This might be for a single instant, but if the receiver is actually moving and moving to, then we need to average the complete fading effect. So it is actually called the ensemble average. So it is the fading correlation is represented in terms of the channel matrix like this. And then from there, we can actually find out that this one component of this complete fading correlation is, as I was saying, that it is dependent on the interaction between the antennas, and we need to find out the pattern-based correlation between these multiple antennas. It can be in the receive side, it can be in the transmitter side. So one of the ways it was defined in the earlier books by Vaughan and Bakes and all. So it is quite channel modeling and the channel correlation, and evaluating the correlation in moving transmitters or multi-antenna receiving elements. So this research has been going on for a long time. And one of the idea that eventually cropped up from all that is to evaluate the pattern-based correlation of these multiple receive antennas. And that is defined like this. So here 1 and 2 represent, let us say I am considering 2 antennas in the, let's say, receive. And I am evaluating the electric field, complex electric field pattern in the far zone due to transmit due to one antenna, and the other antenna also similarly as E2, and first antenna as E1. So when we are having these two complex patterns, we can compute the E1 dot E2 complex conjugate, and then integrate, or you can say average over the complete, this complete solid angle. Like when you must be familiar with the spherical coordinate system that is used in the antenna system. So the theta and the phi. So elevation and the azimuth angle over the complete range, that is theta varying from 0 to pi and phi varying from 0 to 2 pi. You are actually integrating this product, that is E1 dot E2 complex conjugate. And that is in the numerator. In the denominator side, what you are doing is you are calculating the self, you can say, correlation or autocorrelation kind of thing. You can, I'm just trying to map from the language. So mod of U1 square into sine theta d phi, that you are integrating, and again mod of E2 square. So the idea is that this like correlation, when we are trying to find out, let us consider a very simple case. I am just doing all this to, I will not go into the detailed math. I am just giving you the idea that how you can actually see what is happening. So you can consider the case that you read in the textbook, that two Hertzian dipoles, if I am using them at some distance, these formulas are directly available in your textbooks. You can find out that, okay, this is the element pattern due to a single Hertzian dipole that is, let's say, polarized around the y-axis. So this is how the element pattern depends in terms of the function, in terms of theta and phi. So when we have the element pattern due to two such antennas, two such infinitesimal Hertzian dipoles, we can actually find out these products that I was saying, that E1 dot E2 conjugate you can find out. And you can also find out this mod of I square sine theta d theta d phi. And that gives you, eventually you can see that there are certain integral terms that are coming, that complex integral. So why I'm saying complex, because you can see that this is e to the power j k d cos theta, this term is there. So this is a complex function. And there are some weighting terms that are, or weighing terms, as I should properly say, that they are there in terms of the function of the theta and phi. So you can actually now map this complex correlation between the two antennas in terms of the J1 and J2 and these integrations. So what is this J1 and J2 again? J1 and J2 represent the current on these small Hertzian dipoles. So what I was trying to show, I mean, the maths, there is no need to like do it right away, but the idea, I was just trying to give you the idea that this field-based correlation coefficient, there is a way from your textbook knowledge only that you can actually map it with respect to the antenna currents. Only thing is the effect of this angular integration, that is all absorbed, you can say that absorbed in this C12 and C11 and C22 over here. Now C11 and C22 that we found out, like I mean, after some steps, this particular integration, this is, you can solve it analytically, and you can find out that the result becomes 8 pi divided by 3. So only this particular integral on the top, that is on the numerator side, that depends on the spacing between these two Hertzian dipole elements, like how much they are separated in space. And I have mentioned like the distance, like if it is, let's say, d, as you can see from the figure, this is located at 0, 0 minus d by 2. This is located at 0, 0 d by 2. So spacing is d, and I normalize it with respect to the operating wavelength, that is the lambda. That is at which frequency we are calculating this E1 and E2. So this is just for one single frequency I am calculating E1 and E2. So at that frequency, what is the value of lambda? And then you can find out what is the value of d upon lambda. So this is only the integral that needs to be solved. And you know, this is not very like straightforward integral, like it is having e to the power j into twice pi into dn into cos theta. So this will, if you expand it in terms of the spherical harmonics, it becomes more and more complicated. So you can actually see that how the correlation between these two antenna elements are depending on this function C12. And at the same time, it is also depending on what is the current. But since this term is on both like numerator and denominator, it gets cancelled out, and only thing that remains is how much phase difference is there between these two currents. So the amplitude of the current in determining this correlation coefficient is not that relevant, because it is getting cancelled out. But the phase part is indeed, it is having some relevance. So that is the thing that I wanted to highlight. Now the second point, if you, let's say, you ignore the impact of the antennas, if you consider that, okay, instead of these Hertzian dipoles, we are only having isotropic antenna elements which do not have any polarization, like polarization less isotropic antenna elements, which we generally use when we study the array factors in our textbook. So when we find out the antenna array factor and the pattern multiplication, we generally do not consider that all the elements in the array are of the same polarization, and we find out the array factor through considering this, you know, these isotropic elements, assumption of these isotropic elements. Now, if you try to find out the correlation using only the isotropic elements, you will also get something, some expression out of that. But if you plot it with respect to distance, you can see that without the element effect, it is slightly like the value is slightly less as compared to when you consider the effect of the element polarization over here. So that is what I wanted to highlight, that all the polarization calculation, all the correlation calculation that is done without considering the element effect, the antenna effect, like the pattern as well as the polarization, they will give some value, definitely that will give you some limit to design the system. But on the very simple level, you can see that there is a difference. Like this is a most simple case that you can think of. This is just the Hertzian dipole that you study in the textbook, and we are locating it far away. And just their effect is changing the correlation in a certain way. So my point is that it was one of the motivation that we need to actually have some algorithm that also takes into account the antenna properties, the antenna current and its pattern and the polarization correspondingly into this correlation. Now, another part is when we try to find out, like measure the properties of a MIMO system, we generally follow the idea of this reverberation chamber that is there. So which involves, the measurement equipment in an urban environment and moving it around in a indoor environment. It becomes, if we do in this way, it becomes tedious. So reverberation chamber, it actually, instead of measuring in an anechoic chamber, we use a metal cavity which can support many resonant modes, and they have the movable stirrer. So in that way, we actually mimic the scattering or the indoor propagation environment. So some details of the reverberation chamber is there. So how it is done is the measurement frequency at 900 megahertz. There is 6 monopole array and the separate reference dipole. This is just one example that I'm showing over here. So, and the head phantom is also located and cell phone is there. So this is how the characterization of the cell phone in actual life goes into. But not all institutes can maybe support like the reverberation chamber. I am aware of one such chamber here in IISc, but it is like a practical measurement. For doing this, we need to join hands with the industry and maybe take help from the industrial partners. So in the simulation level, what we can do is we can like do this multipath modeling, by actually doing some of the analytical calculation or mathematical post-processing on the radiation patterns that we are calculating. Because if we have the reverberation chamber, then we may not have to go to all these tedious mathematical things and all those things, because that gives you a certain fair idea about how the system will behave in a real environment. But if you are designing an antenna MIMO configuration and you want to find out that how its properties would be when operated in a practical propagation environment. So the formula that I showed to calculate the complex pattern band correlation, that is also not the general formula. That is only valid for the isotropic reference environment that I am mentioning over here, where the assumption is that from all directions over the unit sphere, the signal is coming on your receiver. But it might not be the practical case. You might be holding your cell phone and signal may come from a specific direction. And it can, like the angular way how the signal is reaching your phone, the angular distribution, probability distribution, that might be different. So one such thing is naturally, this is one case that people generally consider, that mobile terminal oriented arbitrarily relative to the direction in horizontal plane. So people say that the azimuth angle is uniformly distributed, but the elevation angle might not be uniformly distributed. So there could be a Gaussian elevation distribution factor into there. So this is where we are not again operating, but in simply designing the antennas, we are moving into the other side, the propagation aspects, which is inside the APS. I should say, like APS is not only about the antenna design, that is the propagation research aspect is also equally important too, because eventually if you want to design a complete system, you need to take care of all the things. So in that kind of scenario, what we do is we try to define the correlation coefficient by incorporating the effect of these statistical angular probability distributions of the incoming signals. And there is a factor known as the cross-polar discrimination, and all those things are imbibed in the complete mathematical formula. So, I mean, for the sake of time, I may not be like going into detail, but just to give you the idea that what happens, that when this is the general case, now there is a specific case, is, as I was saying, that Gaussian propagation environment is there. And then there is also the isotropic propagation environment. If we consider the isotropic propagation environment, then this factor p theta and p phi, which I said that the angular probability distribution, they will become 1 upon 4 pi, because 4 pi is the complete solid angle, and I am considering that from any direction that it can come. So p theta and p phi becomes 1 upon 4 pi. But in a practical situation, it may be biased at some angle, theta v and theta h, that is for the theta component and the phi component, the incoming direction, they could be biased at some side. So that bias is actually incorporated in this mathematical function. So this is how the complete propagation calculation of correlation coefficient goes into. When we consider this formula for the isotropic propagation environment, people have actually, there was a research paper in 2003 in Electronics Letters. So that actually people have found a way to map that formula, that is the correlation coefficient for isotropic propagation environment, that can be directly mapped into the scattering parameters, that is the S parameters that were measured in the antenna terminals. So that makes life actually very simple. If you can measure the S parameters, you can quickly find out, because S parameters using a network analyzer, you can find over a wide frequency range. So you can quickly calculate the correlation coefficient over a wide frequency range using simple measurement of the S parameters. So you don't need the reverberation chambers, you don't need the complex post-processing techniques. But there is a catch, that this formula is only valid for isotropic propagation environment. So this is just a formal proof. I have not gone into I'll not go into the details, but this can be formally proved that how these two formula, that is the correlation coefficient for isotropic propagation environment, that can be found out from the scattering parameters of the two antenna ports itself. But this is not accounting for, this S parameter based formula is not accounting for this p theta, p phi and chi, all these effects. So again, we are back to square one, that if we are trying to characterize our antenna, whatever we have designed, for a real life propagation environment other than the isotropic one, then we might again have to go back to this pattern based correlation calculus. That is why many of you who might be working on the MIMO antennas and sending your research papers out in different journals, I'm mostly talking from the students and the research scholars. So there is a comment that you try to calculate the, we have all encountered that, I have myself encountered this comment, that this is generally there, that you need to calculate the correlation coefficient using the pattern based formula. So just the reason that I wanted to share with you, because pattern based formula, this is actually more general and it can be applied. You can actually take into account the real life propagation factors and calculate the correlation coefficient. And this is an alternative way for people who are not exactly having the reverberation chamber for their antenna characterization. If the chamber is there and you have the proper measuring facility and proper expertise to operate over the chamber, you can characterize your cell phone antenna or access point based antenna system directly experimentally. But if that is not there, you only having the pattern based measurement capacity and still you are trying to model the antenna performance in a real life propagation environment, then you need to follow this particular formula and do the corresponding post processing. And by S parameter post processing, you can quickly do the referencing that how the system will behave in an isotropic propagation environment. But it might not be the best way to look into the system. So the problem with this calculation for correlation coefficient over a wide band, fairly wide band at discrete frequencies through the patterns, it involves a lot of tedious process. Like you need to find out the patterns and at the same time you then need to post process. So pattern measurement is again critical, and simulation also. You need to find out the there in CST there is a way, but it can be done the process is same. Like you they generally take out the radiation patterns and then use this formulation. And that we cannot really, when using this formula, if we are trying to optimize the antenna shape and the antenna current, that is not really possible through this formula, because we are not using the link of the antenna current with the patterns. So to have that link, that is, we want to, like, from the, let's say I'm considering a black box type of thing. So the input, if I am having only the antenna currents, and then the output I am having the correlation coefficient over for a generic environment, if that is the output, then we can actually devise a way, if we find a link to get from the first point to there, that is from the antenna currents to the complex correlation in a general multipath environment. If we find that link, then we can be also reverse engineering the thing, like we may be equipped with a technique to reverse engineer the antenna currents to get a specific correlation performance in a specific propagation environment. So it is important to establish this link, this forward link, so that we can actually think about some ways to find out the backward problem. So that is why there was a significant amount of research was done by like the group in Royal Military College, Canada, involving Syste and Professor Antar. And later on, I also joined there for some time. So we worked on a concept known as the cross-correlation Green's function. But the idea is just the way that I mentioned, that we wanted to calculate the far-field correlation through the current distribution. Instead of computing the patterns, if we can directly map it with the current distribution. And what is the advantage? It is called Green's function because it is actually operating between two dipoles, like two basic dipoles, Hertzian dipoles. We are getting the response for all the polarization combination. And we can actually map any complex current distribution by spatially sampling them in terms of infinitesimal dipole arrays. So that is the idea that was there. And like you can see that we have worked on like several manuscripts like which are published in the Transactions and AWPL. And actually one of the fundamental books is also there, that New Foundations for Applied Electromagnetics, the Spatial Structure of Fields. So yeah, this is me, and you can see Syste and Professor Antar over there. So we worked on we kept on working on this and developed several techniques, like how to use the CGF technique over the massive MIMO system and how to analytically find out. So in the context of massive MIMO, it also becomes very much important. I previously showed that massive MIMO, how the antenna is built and stuff like that. But the uplink channel modeling, most of the textbooks, I'll not again go into the detail, but the uplink channel modeling, the standard textbooks mostly consider the elements in the massive MIMO array to be isotropic. So again, that was not that gave you some idea, but that did not give the idea about the polarization and the dual pole elements which are normally used in the base station, how you can characterize. So all these aspects we tried to report, and this work in 2 years back, it got accepted in AP letters, Antenna Wireless Propagation letters. And we worked on the co-located dual polarized massive arrays and how, I mean, it is actually changing with respect to the azimuth angle and elevation angle. Many research was done, and from the correlation coefficient, how you can actually evaluate the channel models. So I will not go into all these technical things because time is limited, and I would like to keep some time for, let's say, interaction as well. So another part that we extended this was the analytical evaluation of this correlation, cross-correlation Green's function, because the technique that we were using mostly depended on the numerical integration using some tools in MATLAB, or maybe through our own code, own numerical integration functions. But if somehow we thought that we can find out at least the like evaluation strategy for I mean analytical, so that will actually reduce down the numerical cost. So one part of the work was done, and it was reported in Transactions, that we can actually expand the CGF function in terms of this Taylor series, and we can find out the Taylor series coefficients analytically. So I mean, interested people can see this paper that we used the beta and gamma functions, and it mostly mathematics kind of thing, and how you can actually eventually design like algorithm that uses all these things and reduces down the computational cost a lot. So originally, like just to show you how much reduction in terms of time. So the proposed algorithm using the analytical formula, you can see that using the exact formula and numerical integration, it is computing in 5 minutes. Same system, like 256 element massive MIMO array. But when we are using our algorithm, then the time is actually getting reduced to 7 seconds. So almost 98% reduction in time with no loss in the accuracy. So, but this is, I would not say that this is the end of the road. This is just for one special case that we derived. So work is in progress in the other parts. So now, before I coming to the concluding parts, I think, so I'd like to request, so Dr. Priyanka, how much time do I have?
Sir, we have your session till 11:15.
Okay, 11:15, right? So I'll try to wrap it up by 11, and then we can.
Yes, sir. We can have discussions for 15-20 minutes. We must
okay. Thanks. Yeah. So well, so far I was talking about different aspects. I hope that you got an idea about the different things that goes into the mind of a MIMO antenna engineer. You can say that I talked about how to design multiple antenna systems for the base station, multiple antenna systems for the handset, and then how to characterize the correlation between these multiple antennas. But in all these cases, like the handset, base station, or the access point, some of the part I also described access point antennas. So in these cases, it is either like the transmit side and the receive side are like far apart. I mean, the user is at one place and there is a base station at the different. So the complete MIMO system is actually combining the user and the base station, or user and the access point. So it is like that kind of distributed. But now I will be talking about a technology that where the transmit antennas and the receive antennas are actually located in like the same, like you can say, same system it is located. And the application is also becoming different. It is now more towards the radar, like radio detection and ranging. And the MIMO concept, that is use of multiple transmitters and the multiple receivers, that can be used for the like MIMO radar. So people can ask that what is the advantage that you are getting out of this? So just to come to that part, I wanted to go from a little bit more fundamental. So, when we talk about a radar system, there is one metric, that is the angular resolution, which defines the ability of a radar system to separate the objects at the same range and different angular position. So if we are having a single transmitter and single receiver, there is one thing, but let us say considering a single transmit and two receive elements are sitting over here at a spacing of d. So it is called a single input, multiple output radar. So we can increase the number of receive antenna elements. So it is a radar device where there is a single transmit and multiple receive antennas. So here the angular difference between these two elements, you can like phase difference, you can see from the path, and you can geometrically you can find out that it can be mapped with this d, that is the spacing between the two elements, and the operating wavelength like this 2 pi by lambda into d sine theta. And also I am considering only one plane, like only let's say the elevation plane in this case. So you can then find out that if the signal is coming from this theta angle, it is creating like phase offset like this alpha. So that is the reverse process. Like if you find out alpha, then you can actually know that, okay, this is the value of corresponding value of theta. So that is the idea, like to derive, and this alpha can vary from minus pi to pi. Now, in order to get the unambiguous field of view of the radar, we need to have this theta FOV, that is plus minus sine inverse of lambda by 2d. Just because if the alpha can range from minus pi to pi, so you can find out that how much the theta can arrange. You can substitute the value of alpha and correspondingly find out the theta. So this gives the complete field of view, like how your SIMO radar will actually operate. So theta f of v max, that is, you can see, you can now vary the d and find out what is the value of theta f of v. So it actually becomes plus minus pi by 2. So this is the maximum field of view that you are getting from this SIMO. Now, alpha can be reliably estimated by sampling the signal across number of receive antennas and performing an angular FFT. So if you are increasing the number of elements to 4 to 8 and things like that, and you do the angular FFT, again, I mean, I will not go to the maths, but if I go from this, then like, you know, you can find out that 8 receive antennas, it is actually giving 2 distinct peaks, but for same thing for 4 receive antennas, you are not getting. So these things are there. So the direct approach of improving the angular resolution of SIMO radar, it actually means that we now need to increase the number of receive antennas. So this was the idea. But each of these receive antennas, they require a separate chain, separate set of systems, LNA and stuff like that, you can see. So that increases the cost of the system. So that is why there was this technique that instead of using, like I'll not again go into the mathematics, the same thing I wanted to prove mathematically, that how the phase shift across the consecutive receive antennas that increases the resolvability and the angular resolution. The formula, it can be proved, and you can actually find out from the application note. So the only thing, I mean, just takeaway point, ignoring the maths, is basically that if you increase the number of receive antennas, the spatial resolution actually increases. But same type spatial resolution that can be achieved from a single transmitter and 8 receive antennas, you can achieve by using 2 transmitters located intelligently and 4 receive antennas. So the receive chain cost is actually getting reduced. And how it happens, there is a concept of the this multiplicative increase. This corresponds to the virtual array concept, and the number of virtual when you find out the corresponding virtual array, that actually will give you how much improvement you will get in the angular resolution. So the same thing, like this system and this system, they, like you can see that the 2 transmitters separated by this distance and the receiver separated by d, and same virtual array can be realized by this system also, 2 transmitter separated by d and the receiver separated by 2d, but you can see the size is increasing. So generally, to make the system compact, we would prefer this, because ultimately both of them are giving the same virtual array. Now this discussion I did for only one elevation scanning. Now there is possibility of using multiple transmitters in this fashion and design this azimuth and elevation estimation capability, and it gives a 2D virtual array. So this is a 1D array, this is a 2D array, you can see. So there is a lot of research that is going into, and for the 1D perspective, how then from the virtual array, how to relate it with the properties. So it is quite similar. You can find out the corresponding steering vector for the transmit antenna and the steering vector for the receiver. I'm sorry for the typo. I think this should be the receiver over here. And then we can find out the steering vector for the virtual array like this. So what is the application? So far I was just discussing in terms of like some theory, and you might think that, okay. So when we talk about the MIMO radar, the things that I'm discussing is MIMO radar with co-located antenna. You can call it a quasi-monostatic configuration. There is also the concept of MIMO radar with widely separated antennas, that is the multistatic configuration, to capture the diversity of the target radar scattering section. So for, I mean, mostly from the aircraft and defense point of view. But when we are talking about the MIMO radar for automotive application, this is one of the chips developed by Texas Instruments. You can see from their website. And you can notice that there is this, just from the previous, this slide, let me just go back. So almost this type of configuration, like 3 transmit and 4 receive. So you can actually notice here that there is this 3 transmit and 4 receive. And these are the antennas that are present over here. They are these series fed microstrip patch antenna based designs. So I would skip this part and maybe come to some of the things that we are doing. And so this is Jogesh, who is working with me here as a postdoctoral research associate at IISc. So we are working on a lot of interesting things involving these MIMO radar systems with co-located series fed patch arrays. So the focus is to improve the impedance matching and SLL and cross-polar level, obtain a wide field of view. And furthermore, the angular resolution performance can be improved by enhancing the, as I said, the virtual array effective area. So one work that he has done, and based on the 3 transmitter and 5 receiver MIMO radar module, you can see that the 3 transmitter antennas are there and 5 receive antennas are placed. And these series fed patch antennas, they are also not equally shaped. There is a special, like you can say, a kind of a modulation, like when we go from one patch to another, the width is actually changing. So tapering, you can say, some kind of distribution is there to improve the side lobe level, because if we are using same type of patch elements, it may not give you the best performance from that. And again, there is the aspect of the cross polar level also for the system improvement. So these things are actually managed by taking care of the antenna design. And then the virtual array part is taken care by the spacing, how to space these antennas. And as you can see, if we place the transmit closer, then receive has to be proportionately spaced even further. Then it would have increased the size of the board. So this design, this series spaced array with modified binomial coefficient for MIMO radar application, this is accepted to be presented in your APSRC. That is going to be mostly, I think it will be virtual at Singapore. So we designed it for like this for 77 gigahertz, and modified binomial tapering was used, and the angular resolution was improved. So this is the type of the pattern that is actually there for this element in 2 plane cards. And then we are also working on another very important practical aspect, that is these MIMO radar modules, whatever I showed, that was an inside view of like TI module, and similar type of designs are here. But these sometimes in automotive application, not sometimes, I think mostly, they will be placed behind a certain bumper. So how the property of the bumper material will actually impact the performance of the radar itself. So that is a very like a system level study that we are trying to do, that using a 2 transmit and 4 receive MIMO radar and placing a curved bumper above it. So how the properties of the bumper material, let's say the permittivity, it could be multi-layer paint can be used over there. But if we are, let's say, considering it to be a homogeneous one with a single permittivity with that shape function over there. So the shape function and the permittivity value, all those things will actually impact the performance of the complete radar. And this is a serious problem. I was discussing with the TI guy on this, that we sometimes design it without that bumper and all those things, but when we install it, the complete performance of the system becomes changed. And that is I mean a very problematic issue, because if they supply it to some customer and then it does not find the correct performance, and if the angular resolvability and all those things goes different, then it might not work as a proper the collision avoidance and all the applications that are there. Why this MIMO radar is used in automotive, to detect how another car is coming and maybe do some autonomous control. So all those things will get affected if the MIMO radar performance itself gets changed just by placing of the bumper. And the bumper material and its paint, everything can actually depend on the aesthetics, and not always the electromagnetic point of view may come there. So the complete the system integrated thought process is coming into picture there. So to do this kind of modeling, I'll not again go into the details. What we were trying to do is use a near field equivalent source model using the tangential E and H field to get from the isolated system the pattern, and using the complex pattern on the bumper, we are trying to find out the effect. So instead of doing the complete simulation will actually take a lot of time. Lot of simulation time will be considered if we are going to use even the present day solvers with a reasonable capacity that can be available in an academic environment. So that is quite time consuming. So that is why we went to time and resource, both the things will be consumed. That is why we went into this near field equivalent source based approach. And this is reported, it is still unpublished. So I'll maybe just give you a highlight, like the change in the bumper permittivity is actually changing how the antenna array ambiguity function, which actually defines the unambiguous field of view. Like this region, this represents the unambiguous field of view. So if that is actually disturbed by placement of the different bumper materials, then the system will not work properly. So we need to think of some ways to mitigate these things and maybe design the bumper by considering these things in back. So before I end, I think I'm almost at the fag end. So before I end, I'll just highlight one quick thing, that I was discussing multiple antenna systems for MIMO antenna for handset and base station, everything, and little bit about the MIMO radars also I tried to discuss. But these multiple antennas and how they are, like you could see that we can have to design the compact system and place them close together. And so there will be a lot of interesting finer interactions that will be happening between these multiple antennas placed close together. So that actually motivated us to work more fundamentally towards how the energy around the antennas, near field energy around the antennas is actually distributed. So we worked on developing a concept on pointing localized energy, and that work last year, it got published in the Transactions, and this year will be a general article, a representation of electromagnetic energy around antennas. Finally, it's coming out online probably in October. So we discussed how the pointing localized energy, which is different from the conventional reactive energy concept, and I mean different in a way that it actually generalizes it into the spatial domain as well. In the reactive energy, we generally don't look into the spatial aspects, but pointing localized energy will go into that directions. So that work will be reported there. So I mean, interested people can see how the historically these things evolved and why we need to go into this type of new definitions. So with that, I'll come to the conclusion of the talk. So first of all, I talked about MIMO antenna systems, the capacity enhancement and the diversity beamforming. I tried to touch upon these things, and 4-element MIMO antenna, some of the design ideas during my PhD, and then I talked about our research. So this I did not cover in today's talk because of lack of time. Maybe some other time I will do. And we then talked about another aspect like MIMO radars and how we can use the CGF or other strategies to get these new design methodologies, and how to characterize the effect of this covering structures and radomes and rectify those problems. These are some of the research. And we are looking into the pointing localized energy for multiple antenna systems that I wanted to highlight. So yeah, with that, I would like to end my presentation. And well, I thank you for listening to me patiently. And yeah, I'll happy to take a few questions before the other session starts. Yeah, thanks.
Yeah, thank you, Debdeep sir. I must thank you for enlightening us and the participants about the very basics to the ultra modern trends in the wireless communication like MIMOs. And I must thank you, and we will surely do the discussions. But before that, with great glad, I must inform you and the participants that during the session, Dr. Sudhakar Rao was also present, and he graced the session with his presence. So I welcome Dr. Sudhakar Rao.
And, hi, Dr. Rao.
Oh, thank you, Priyanka.
You're most welcome, sir. Thank you.
Yeah, very good talk, Debdeep, and very inspiring talk. And I know your work and always high quality work. And
thanks a lot. Yeah,
yeah, the MIMO is very important, especially nowadays. And actually, this MIMO work we started probably in 1996 or 97.
Right.
When we built Thuraya satellite, which has 120 beams,
right.
And 200 beams and 120 elements, and both on transmit and receive. So imagine that you have 120, 200 and transmit beams, 200 receive beams, and the design is a bit challenged. So I think we did that. All the signal processing is very important.
Yes.
So all the processing is done digitally. So, so each of these element actually complication is each of these beams use multiple elements. So it's not just a simple MIMO, it's a sort of complex MIMO.
Complex
And
MIMO.
now we are actually working on maritime satellite, where I think we need to communicate from 1 gigahertz to 60 gigahertz. I think I presented some work on my talk, which goes up to 100G, not 5G. So you can imagine the capacity of the system you need to have and the complexity of the antenna. So these are some practical applications. So I think what you presented theoretically is develop the theory is very important. And I hope all the youngsters follow the work and work on basics first, learn the theory, and then slowly try to apply the theory to practical problems like wireless systems, like cell phones, and going beyond cell phones, and maybe more complex systems. So thanks, Debdeep, for a very good, inspiring talk. I didn't follow completely, but I think I sort of followed maybe 50% of the talk.
Yes, thanks very much, Doctor. I think the thing that you mentioned is actually one of the point I tried to also communicate at some point, but maybe that many of these technology, I think what are used in the cellular or these things, they are already somewhat already developed by the defense and the space industry, and many of these multi-antenna technologies, or these whatever people are calling in for 5G as the massive MIMO, those massive antenna elements and the digital processing of the streams and the backend technology might already developed in the defense and space. So something people are in the commercial sector, people are trying to bring in. But yeah, I think understanding the basics is very, as you said, is important to start some new research or contribute to the already existing industry. So yeah, that is, Thank you once again, Dr. Rao, for your comments.
Oh, you're welcome. Very good talk. Thank you.
Yes, sir. Now we should take question answers. So I think
I can see in the chat box.
Yeah, we can see that.
Yeah. Okay. Yeah. So can you just read it out?
Yeah, sure.
Yeah, sure.
One question is there: in MIMO antenna design, ECC plays a very vital role. If we design 4x4 MIMO antenna, whether we have to check ECC for all the antennas or any one antenna?
Yeah, okay. So, good question. So basically, since you are having a 4-port, let's say 4-port system, so ideally, the thing is to calculate the ECC, that is the correlation. You need two, set of two antennas, right? So you can say that from 4C2. So you can imagine how many, 6, I think you need to calculate the total number. If it's 1, 2, 3, 4, then row 1, 2, row 1, 3, and row 1, 4. Similarly, 2, 3, and 2, 4, these things and 3, 4. So generally for these symmetric systems, we need to calculate 6 type of envelope correlation coefficients in general. But non-symmetric. But then if it is a symmetry, then it might be that 1, 2, and 1, 4 are actually same. So you need to only calculate 1, 2. And maybe 1, 3, and 2, 4, they are also same. So in that way, you can imagine it will get reduced depending on the symmetry of the system. Yeah.
One more question is there. While calculating channel estimation in MIMO systems, what are the major parameters we have to consider?
Right. So, channel estimation, again, it's another problem. So I can say for your, if you want to, you have some antenna, large antenna array, and you want to find out the uplink channel and things like that. Then again, you need to find out the correlation coefficient, and from there are ways to actually map it into some practical channel modeling. So that is it. But I think channel estimation problem, it is, again, I will not go there. It is more a communication problem, communication system problem. Yeah.
Yeah. So one question is there. Please tell some insights on characteristics modes.
Yeah, well, I think characteristics mode, it is a different topic from today, but I can quickly say that when let's say we talk about very simply, I will try to, maybe it could be not very much technical, but the way we look into the resonators, let's say a cavity we have. So it is a non-radiating cavity, then we can actually find out the corresponding modes. And we try to see that how the E and H field distribution and stuff like that inside a cavity. But if we have a radiating system, and then like it is a kind of open boundary problem, and there are techniques developed from the times of Harrington, and many other people have worked. I am not an expert in characteristic modes, but that open radiating mode, open radiating structures, there, that current, you can actually find out the characteristic modes, and from the characteristic modes you can actually, the idea is you can see that where to excite the particular structure. Like if there is a given structure, the way we try to go is we try to, from our intuition or the judgment, we try to see a feed location, and the feed location we change, and we try to find out the radiation and all those things. But instead of going that way, because for practical structures, it might be time consuming for the industry. So generally nowadays, there is this characteristic mode solver available in CST, and people try to find out the characteristic modes and the modal indices and stuff like that, to actually find out that what are the useful radiating modes right from the structure, and where to actually tap into there to get the radiation patterns. So this is the general idea behind the characteristic mode, but the mathematics and all, I mean, probably right now is not the time to go into the details. So this is the, like, I tried to give some basic idea about the characteristic mode.
Yeah, thank you, sir. One question is regarding measurements. So participant is asking, my antenna is 8-port, but suppose 2-port VNA is available, then how to test the antenna?
Yeah, I think, well, so this is a kind of practical problem that we all face in academic environment mostly. So if we have a 2-port VNA, then you need to connect actually the other antenna ports to match load, and then combine, like let's say 8-port is there, so you can 2-port VNA, so you can actually combine the other 6 ports step by step, like with matched loads, and then calculate the S parameters for the 2 ports, and for other port combination you do that, and then intelligently combine all the data. So that is the thing that is generally done in most of the academic labs, and when we design this 4-port, we also followed the same procedure. But now if we want to build a complete system, then you need to design some kind of switching mechanism that will actually switch the signal from between the different ports. So there are ways, I mean, you can use, let's say, FPGA based systems or things like that. Those things need to be added in between the VNA and your multi-port antenna, if you want to operate all the ports in a real time or in a time duplex or that kind of fashion. So that technology has to be interfaced in between. But for the characterization part, it is just doing the lumped match, like lump load termination and doing the respective things. Yeah.
One more question is there, sir. How to calculate CCL for 8-port MIMO?
Yeah, well, so yeah, so I think there is a formula already existing. Like if you calculate the ECC, then from the ECC matrix, there is a way to, like, there is a minus log 2 into minus of logarithm of 2 and determinant of the ECC matrix that is there. So once the ECC matrix is found out, it will be a 8x8 ECC matrix. So from there you can find out the corresponding CCL using the determinant evaluation.
Yeah, thank you, sir.
Madam, can I ask one question?
Yeah, sure.
Sir, this is regarding in the research, whatever in the academic research, we use some of the materials for the whatever the presenting the papers and all this.
Right.
So especially with respect to antennas. So when we go for the industry, so if you take a mobile application or something, what are the materials used for the antennas there actually?
Yeah, well, so I will not be able to give you the first person because I have not worked there. But generally, what I hear is that about the Rogers substrates and the Taconic, and I mean maybe like I think Dr. Rao is the best person to because he has got loads of experience in handling the antenna industry for a long time. So the way we look into it is should be like in the academic environment, we sometimes go for the low loss FR4 type material to simply I mean, what should I say? Like simply evaluate our concepts, whether it is working or not. But to make a proper military grade or commercial grade object, then you need to go for very good substrate. So Rogers is definitely one that is coming into my mind, and Teconic are there, and many other like people from industry will be able to comment better on that. Now regarding Rogers, there is a way to get free samples for academic purpose in academic institutes also. So if you are interested to do that, like characterization with the Rogers substrate with a low loss and good permittivity, like variation over the, like, well, I should say constant permittivity over the frequency range, then you can get those academic free samples by contacting the company directly. Okay.
Thank you, sir.